And yeah, thanks for the invitation. It's nice to be back at CITA. You know, I don't have too much experience yet with these online talks, so I'll see how that goes. So let me share my screen. Good. Can you see my screen?
Looks good.
Okay, great. Okay, yeah, as Jennifer said, I'm going to talk about galaxy formation simulations, specifically cosmological simulations. And the idea is to give you a bit of an overview of what we and our collaborators have been doing over the last, well, 5 years or so. And yeah, so I hope I can convey, yeah, what was the progress over the last 5 years. Now, to get started, it's probably not necessary for this audience, but I just want to give a quick overview of what we actually try to achieve with these simulations. And, you know, in a nutshell, our goal is written on this slide. So we really strive for a theoretical and computational framework to understand how structures and galaxies in the universe form and evolve, starting from the smooth initial conditions of the early universe. So this one sentence more or less describes what we try to do. Of course, there are different flavors of these simulations, but if you speak about structure and galaxy formation simulations, this is what most people understand under that field. Now, to do this, you know, of course, you can do a lot of things in perturbation theory and higher order perturbation theory, but if you really want to study nonlinear evolution, the complexity of the problem typically requires numerical calculations, which are then these cosmological simulations. And these days, these simulations, you know, they model dark matter, dark energy, and baryonic physics. They include now a wide range of different physical processes that are relevant for shaping the galaxy population. And over the last years, or the last decade, more or less, people have also put a lot of, you know, emphasis to perform these calculations with rather accurate and efficient numerical methods, with the goal to simulate ideally statistically significant volumes at high numerical resolution. So what you really want is not just a single galaxy at high resolution, and also not just a few hundred, but really tens of thousands or hundreds of thousands, to really get a good statistical sample that also, you know, at least gets close to what we can do observationally. And once you have such a sample of galaxies, then we can do mock observations to really do a detailed comparison to observation data. And of course, the idea is that we, through this process, constrain our models and refine our models of structure formation. And structure formation really means here a lot of things. It means understanding the baryonic physics, but also it means, you know, studying and exploring different models for dark matter and different models for dark energy. So just to see how galaxy and structure formation works in these different models. Now, for this problem, I want to stress again that it's really, especially for what I just outlined, it's typically not sufficient just to do isolated small-scale galaxy physics-related problems. So we really need this large sample of galaxies to really compare to observational data. So in a nutshell, this is what we try to do. Now, there are different approaches, as I mentioned, in these for these galaxy formation simulations. There's this so-called bottom-up small-scale simulation approach, where you really simulate a lot of you know, galaxies at high resolution through zoom-in simulations. And here's an example from the fire simulations. That is, of course, great because you have very detailed models for the physical processes because you have the numerical resolution in the galaxies. But on the other hand, as I mentioned before, then you are rather limited in terms of the statistics, because you cannot have a large number of these galaxies. You typically have a few hundred, and that's more or less the sample you have. On the other hand, there's this top-down large-scale simulation approach where you have a large volume that you uniformly sample, typically, in terms of your mass resolution. That gives you lots of statistics, but of course the downside here is that the models that you use for the baryonic physics, so for example, for stellar feedback, AGN feedback, star formation, the physics of the ISM, and many other things, has to be, or is essentially less detailed than what you can do in these small scale simulations, simply because you don't have the numerical resolution to model this all in detail. So naturally, there's kind of a scale gap between these two sets of simulations. And one of the goals of galaxy formation is actually to make this gap as small as possible. Yeah. Now, over the last 10 years, there have been a lot of different simulations, a lot of large simulation campaigns. Now, this to some degree became now, like an industry. And so what you see here is kind of an overview of the different simulations. Most of them have been done in the last 10, 15 years, where we split the simulations in Zoom simulations and large volume simulations. And then there's another split in dark matter only and dark matter plus baryons. So there has been a time not too long ago where, still a lot of people have run pure dark matter simulations. I mean, there are, for example, the famous Millennium, Bolshoi, G-Halo, Aquarius, and all these simulations that have been run dark matter only, pure n-body problems. And a lot of these simulations were instrumental to establish a lot of interesting results, like, for example, the things like the NFW profile and other things have been discovered in these n-body simulations. But nowadays, things have shifted a lot to these hydrodynamical simulations. And here on the right, you see some examples. So in the Zoom regime, I mentioned already Fire, but then there are many others. And this list is by far not complete. There's also Nihao, Apostle, and Auriga. And then these full volume simulations like Magneticon, Zimba, and many others. Again, this is by far not a complete list. It's just to give you an idea. I mean, I said that a lot of simulations are now with hydro. That doesn't mean that n-body only is not useful anymore. So there's still a lot of interesting problems that you can do with n-body simulations. Like, for example, what is the structure of the smallest halos that, or the internal structure of smallest halos that form in CDM, and other questions related to that problem. So there, it's still very interesting to do dark matter only simulations. And of course, dark matter only simulations also have the advantage that you have a very clean problem. Yeah, so at the end of the day, it's only gravity. Whereas if you couple things to hydro, then a lot of other effects come into play, and sometimes it's very difficult to disentangle all these effects. So in that sense, n-body also provides a very clean setup to study certain problems that are still relevant today. But you get from this slide already that there's a lot of things happening and a lot of simulations have been performed. And of course, if you would sum up the amount of CPU hours in this slide, it would be really a quite large number. I mean, Illustris TNG, for example, alone has used significantly more than 100 million CPU hours. So you can imagine if you add this up, this is a quite substantial number here. Now, what I want to talk about in the talk after this quick intro is actually three different things. So I first want to talk a bit more about these large-scale cosmological simulations. So this top-down approach, so not the Zoom simulations, but really coming from the large volume and uniform sampling, and just show you what you can do with these simulations these days. And then I want to talk about two frontiers in computational galaxy formation, frontier 1, that I call here the astrophysical frontier, and then frontier 2, the cosmological frontier. And I will talk a bit more about this later, and then I will have some conclusions at the end. So let's get started with the these large-scale cosmological simulations. And this topic is, pretty much related to this Illustris project. So I should have, as a disclaimer, of course, say that a lot of the results here that I'm showing are heavily biased to our groups. Of course, there's a lot of other groups that have also done excellent work, but I'm mostly focusing here on our group. So Illustris, along with many other simulations, about 5 years ago, started essentially this, well, I wouldn't call it revolution, but these set of successful large-scale hydrodynamical simulations that were for the first time able to reproduce a lot of properties of galaxies for large samples of galaxies and very well resolved sets of galaxies. Yeah? So it was the combination of new galaxy formation models, new numerical schemes partially, but also the increased computing power leading to larger volumes at high resolution that essentially enabled all these projects like the Eagle simulation, Illustris, and Horizon AGN. Now going a couple of years forward to 2018-19, we now have this new set of simulations, Illustris TNG, which is the follow-up of Illustris. I don't want to talk too much about the details here because, I guess many of you have heard already some talks about this. So the idea here is that TNG has more or less a similar galaxy formation model like Illustris itself, but there were some significant model improvements, especially for the treatment of AGNs and other things that actually led to a better performance of the model in terms of the agreement with observational data. Illustris TNG itself also is not just one simulation, it's in fact 3 simulations. It's this TNG 50, 100, and 300, where the number just always encodes the side lengths of the simulation volume. And you can see at the bottom right, this is a picture of the galaxy. So in the left, it's in gas, and in the right, it's stellar light. This is a typical Milky Way-like galaxy in this TNG 50 box. And you can just visually see that this has actually pretty good numerical resolution here. Good. Now, this all, just as another comment, so this all, both Illustris TNG and some other simulations have actually been built up of this out of this galaxy formation model from Illustris. And Illustris itself has been, a multi-year effort. So sometimes people forget this, that we really worked for quite some time on this, and that there were also a lot of people involved. Yeah, so there's, for example, here Deborah Siachki, Dusan Keresh, Paul Torrey, Dylan Nelson, Simeon Bird. So a lot of people have worked on this and contributed to this. And then these newer projects like Auriga from Robert Grant and the Fable simulations from Cambridge, they all built on this. So there's a continuous effort essentially in that direction. And there are now new simulations coming up like Millennium TNG, which is also based on the TNG model and is essentially simulating the whole original Millennium volume with the TNG galaxy formation model at very high numerical resolution. So the bottom line is it's just a very long-term effort essentially that we are after. Good. And just as a last thing here, of course, the numerical resolution also plays a huge role, and it's actually quite interesting if you look at hydrodynamical simulations and also in body simulations and plot the number of resolution elements as a function of time. You can actually quite nicely fit this with the exponential, with a doubling time scale that's actually slightly shorter than what Moore's law predicts, because also a lot of algorithmic improvements have been put into these codes. So it's really quite rapidly evolving. And I don't have the point for this Millennium TNG simulation here, but that would also nicely follow that exponential trend here. And as most of you might know, for the n-body simulations, we are since many years now in this multi-trillion particle regime. Yeah, so I mean, you cannot even see this here anymore, but this has also developed enormously. Good. So let me show just 2 or 3 slides with results from Illustris TNG. So one thing that is novel in TNG is that we have also magnetic fields now in the simulation. So this is now from a bit of an older paper from Federico Marinacci, who's now a faculty in Bologna in Italy. So he looked here specifically at different types of galaxies. So you see on the left elliptical galaxies, on the right a few examples of spiral galaxies. And then in the middle panel, you always see the gas density and the velocity field. And in the right, the bluish panels, these are the magnetic field strength. And on top of that, the topology of the magnetic field. Yeah. So this is just to illustrate that you can really see now very detailed structures in the magnetic field. And I don't have the plot here, but you can also check, for example, the magnetic field strength in these systems and also make Faraday rotation maps and actually convince yourself that the predictions in terms of the field strength actually in agreement with what we know observationally, at least within the error bars. So also this aspect is now working pretty well. Then you can also...
I have a problem. I have a question.
Yep, sure.
Yeah, sure. Just about the strength of the magnetic field. So as far as I remember, the dynamo to generate magnetic fields, which is quite resolution dependent in the numerical simulations. So how did you do that in this?
Well, there have been, I mean, so there have been a couple of papers led by Rüdiger Packmore, who has, with the same MHD implementation, looked into Zoom simulations. You know, because you're right, it's a bit, I agree, we don't have the super high resolution here, and you might wonder, how can we resolve all these dynamo effects? But it turns out that the growth rate is correctly captured here. So you can actually see this. If you go to higher and higher resolution, the results actually start to converge. And this has been done by Rüdiger. And he also in detail analyzed the different dynamo effects, the two dynamo regimes in his papers. So there, yeah, you can find all the details. So these are, I think these are 1 or 2 years, well, 2 or 3 years old. And they used the same galaxy formation model, but they did this on isolated galaxies, just pure zoom in, and where they could follow, or where they had the resolution essentially to follow these processes in more detail.
I guess I have confusion, because I thought if you start off with no magnetic fields, the MHD equations still give you 0 magnetic field. So something must be missing how you get.
Yeah, that's true. I mean, we do ideal MHD, but you're right. If you don't have magnetic field initially in the simulation, then nothing is growing. So these simulations, this one and also the ones that I just were talking about, they have a small seed magnetic field, a tiny seed magnetic field that you put in by hand. And then the dynamo is actually, amplifying these magnetic fields. And it turns out that the end results, so the results of the magnetic field strength that you get in the nonlinear regime, are not sensitive at all to the initial seed field. So you can change the seed field by orders of magnitude. It doesn't change the redshift 0 field strength in the galaxies. But you're right. If we don't put a B field in, since we do pure ideal MHD, you would not get any B field, but there is a small seed put in the simulation. Does this make sense?
Yes, thanks. By the way, do you also have plot of magnetic helicity as well?
I didn't look at that, but I think Rüdiger also has some plots in his papers. So I think he checked also these things. I don't know for sure, but you should check his papers. He had 3 or 4 papers only on magnetic fields, and also topology of magnetic fields, amplification of magnetic fields, and Faraday measurements. I don't know whether he also looked at helicity, but yeah, you should check. I don't remember now. But...
Great, thanks.
Okay. Good. Okay.
I also have a question about the magnetic field. So I know that from observations, at least ones that Brian Gensler presented last year, that at least in the Milky Way, the strength of the magnetic field is comparable, but the virial parameter is of order unit. It's about the same energy density as the thermal energy, the kinetic energy of the gas. Is this also what you see in simulations, that eventually you just, regardless of what you start with, just grow until you get to, until you saturate that level?
You mean it's kind of equipartition, or is that what you mean? Or between the different energy forms?
So basically, yeah.
That's more or less what you also find in the simulations. Yeah. So it's yeah, you can check this, what the energy contributions is, and it's roughly as you described. Yeah. Also, the field strength we get is consistent with these measurements within the Milky Way, but also the energy contributions from the different components is as it's inferred from these other studies. Yeah. So that's consistent with the simulations. Okay. Good. Then let me move on. Another thing unrelated to magnetic fields I want to talk about is that you can also use these simulations, and this is some more recent work, to make predictions. So here specifically for JWST, so these are UV luminosity functions from redshift 2 to redshift 10. And we overplot here some Hubble data. Yeah, so you see also some Hubble data. And the point is, that this works remarkably well also now over a wide range in luminosities and also over a wide range of redshifts. Now these lines that you see, they don't come from a single simulation. You remember I showed you these 3 different simulation volumes. So what we had to do here is to cover that dynamic range. We actually patched the different simulations together through some resolution correction procedure. to get this result. Yeah, so this is really what you see here. The simulation results. So this TNG combined here is really TNG 50, TNG 100, and TNG 300 all combined together, and then you can achieve that dynamic range, and that works pretty well. Now, of course, there's one thing that I didn't say when I said it works very well. So there's we have to do dust attenuation here. So the results that you just saw are based on Monte Carlo radiative transfer with dust. So we have to put some dust in the simulations, which is not self-consistently tracked. And this has the advantage that, you know, since we gauge our results essentially towards low redshift UV luminosity functions, so you can then also predict the dust abundance in the galaxies. So this is, for example, here a galaxy in TNG 50 at redshift 2. So I didn't write this, unfortunately, but you know, what you see is actually these dust lanes. So this is self-consistently predicted by matching the UV luminosity functions. And if you turn this around, you can then make arguments how, for example, the average dust to metal ratio as a function of redshift should evolve. So what you see here in the right plot is based on this gauge process that I just described, how we've, based on the TNG simulations together with radiative transfer and dust, what kind of dust to metal ratio we actually prefer, so that we get the UV luminosity functions right. Yeah. So as you know, it's observationally not very well understood how much dust you have in what kind of, or what types of galaxies at what redshift, but you can actually infer this from the simulation by really this gauge procedure that I just described, and that is what we find. And here on the left is actually a comparison to other results that people have proposed over the last 10 years, and you can see that actually our result is significantly steeper than some of those. Yeah, so they have much less of a redshift evolution. I wouldn't claim that means that, you know, that the others are somehow flawed. It's just that what our model prefers, I mean, both the radiative transfer and what the TNG model itself prefers, is just a significantly steeper relation, how the dust to metal ratio evolves as a function of redshift. Yeah, so it's a pretty steep relation if you look at this from redshift 8 to redshift 2. So this is just some other things you can infer through post-processing, essentially, of the simulation. Good. Okay, so that is kind of the things where we are now. Now, for the rest of the talk, I want to talk more about the frontiers and what might be coming next in cosmological simulations. And again, this might be a very biased view. So I just selected a few topics, but this is just to give you an idea what we are currently working on and what we think is quite interesting at the moment. And as I said, I will split this in two frontiers, frontier 1 and 2, astrophysical and cosmological. And we are going to start with the astrophysical frontier. And here I just, again, put this in a sentence here. So the situation we have now with cosmological simulations, and specifically galaxy formation simulations, is that every group, every simulation that is published these days, essentially uses some effective model for galaxy formation that is calibrated, or essentially calibrated in a way that the model agrees on most integrated predictions, meaning that you will not publish a simulation these days if you don't get the galaxy stellar mass function right, or the galaxy luminosity function, or the stellar to halo masses right, or the clustering as a function of stellar mass. Yeah, so all these things are correct if you compare to observations for all published simulations to more or less the same degree. Yeah. So this is very different from what we had 10 years ago, where most of these simulations didn't even get the stellar masses right. Yeah, so there has been a lot of progress, but at the moment, this is the status of all simulations that are published. However, of course, that doesn't mean that we understand galaxy formation. It only means that we came up with some effective models that parameterize galaxy formation somehow to produce a more or less realistic galaxy population. But of course, the ultimate goal is that we want to better understand the physical drivers of these effective models, and also ideally approach a regime of what I would call approximate ab initio calculations. Yeah? So ab initio in the sense that you just have individual stars in galaxies, and you model the feedback in as great detail as possible. Of course, we will never be able to do true ab initio, but essentially reach this regime of approximate ab initio where the individual star is the smallest element. This, however, getting there requires overcoming this scale gap that I mentioned at the beginning, and also refining the physics that we put in these simulations significantly. And so I think this is, again, kind of in a nutshell, the frontier that many groups are now facing and tackling, and in terms of the astrophysics of these simulations. Now, let me come back to this slide. So essentially what that means is what we want to tackle that scale gap here, by having somehow novel, less calibration dependent numerical models. All these models in all these simulations, even the small scale simulations, are calibrated somehow. So of course we want to get rid as much as possible of any calibration process and really have this approximate ab initio regime. Now, if you have such a model, then it has the advantage, especially with the increasing computing power, that you can model large and small scale simultaneously, and then you have detailed effective models for the physical processes, and at the same time you have lots of statistics to compare with data. So that is kind of the ideal regime. You're not very calibration dependent, but still you have detailed physics, and you have a lot of statistics in the simulations to compare to observational data. And of course, there's a lot of groups working on that. And a lot of groups also had already great success there. So I just want to show you what we have been trying over the last 2 or 3 years in that direction. And what we did, and this was mostly led by Federico Marinacci and Laura Sales. So they came up with this new galaxy formation model that's called SMUGGLE, which stands for Stars and Multiphase Gas in Galaxies. So this is a complete rewrite, essentially, of the ISM model of our galaxy formation code that we use. So if you look in detail of what Illustris TNG, Illustris, and many other simulations have used as, for example, model for the ISM and also the stellar feedback, then this goes all back to a model that was already developed in 2003 by Volker Springel and Lars Hörnquist. So it's a very old model. It's a very robust model, and it's ideally suited for these large volume simulations. But now that we can approach smaller scales, we wanted to come up with a new model that is more refined in terms of the stellar feedback and closer in spirit to models like FIRE, for example. So it shares a lot of similarities with FIRE, the basic idea here. So I don't want to go into all the details here, but you see that we have refined stellar feedback, we have refined cooling processes and heating, and some refinements in the star formation. And the goal of the model is not so much, that we want to apply this to Zoom simulations, but that we really want to construct it in a way that we can also use it at the resolutions that are currently feasible in large volume simulations. And so just to give you an idea how predictions of that model differ from what we have used before. So here you see the gas distribution of a single galaxy, a disk galaxy, with this old model that we have used in TNG on the left, which is also a kind of an effective equation of state ISM model, and on the right with this new model. And just by eye, you see that the density PDF is rather different. So there's much more detailed structure here, simply because the model on the left, just per construction, doesn't resolve a lot of these small scale features. It uses an effective equation of state to describe the ISM without distinguishing different phases. And this is different here in the right. And of course, this also has implications for the phase diagram. So if you plot this here in temperature density, then you get this phase diagram here on the left from this old model, and you might wonder what this line here is. So this is effectively the parameterization of the gas on this effective equation of state that's inherent in that model. And this is what I meant, is that by construction it doesn't allow multi-phase gas. So that's now very different in this new model, where you now can have cold star-forming gas, warm gas, hot ejected gas, and so on and so forth. Yeah, so the phase structure is much richer and also, of course, much more realistic, because we know that that's not a realistic, phase diagram of the ISM. So here's a breakdown then of the new model in terms of the different gas phases. So we made here a distinction in cold, warm, hot, and total. And you can see that there's really 3 distinct components in the ISM resolved in the model. So you can see this both here. In the left, this is a mass PDF. In the right, it's a volume PDF. And you can clearly see this. For example, you nicely see the volume filling factor of the hot phase here, and so on and so forth. Now, another feature of this new model is also that it self-consistently generates outflows and, of course, also inflows. So what you see in the 6 panels here on the top is actually phase-on and edge-on the time evolution of a galaxy in the new model. And you can see that above the plane, you get this, these outflows going. Now, in the old model, you don't see any of that. So there's no outflow. So these outflows in the old models had to be put in by hand. So there's a specific wind loading mechanism that has been put in all these simulations like TNG that actually took care of galactic outflows. So this is done self-consistently in this new model. So this is simply coming from the stellar feedback here. Okay, and then of course you can also measure this. So these are, for example, in outflow and inflow rates for these isolated galaxies in units of solar masses per year. And you also can look at then what is even more interesting at the wind mass loading, which is often just called beta here, again as a function of time. And this is a Milky Way-like galaxy in terms of its setup and its mass, and you can see that it hovers around or between 1 and 2 here, which is kind of a realistic, or what we believe is a realistic wind mass loading for that kind of system. Of course, this is strongly galaxy mass dependent, but for that specific system, this is what we believe is a realistic value. And last but not least, you can also look at the star formation rate and the integrated stellar mass. And this is now an interesting plot for a couple of reasons. So first of all, the gray line here, if you just focus on the left panel, the gray line here is the line without any feedback. And this is a well-known result. You get far too much star formation because you don't have any feedback. And then the colored lines are now interesting because the orange line, which is called here SH03, so this is this old effective model. And you can see this is not bursty at all. It's just a very smooth star formation rate because of the smoothness of the ISM that is intrinsic to that model. And then the colored lines, the blue, red, and green, are different numerical resolutions of the new model. And now you see 2 things. The first thing is that, of course, this is much more bursty, but nevertheless, it's if you would average that, it's more or less at the same level as the old model. But what's even more interesting is that the different resolutions, low, medium, and high, you can also see this here in the stellar mass, they roughly converge to the same stellar mass. And now the low resolution here is the resolution that we can achieve in uniform cosmological simulations. And so don't forget, I said at the beginning, we don't want this model to only work in very high resolution zoom simulations, but also in really large volume simulations where we do not have this exquisite numerical resolution in a given galaxy. And this is really the blue line here. And the fact that the blue line agrees, or that low resolution result agrees, at least in the total stellar mass, with the medium and high, is at least encouraging that this model should also work in large volume simulations. And I should say the difference in terms of mass resolution between these 3 resolution levels is each time a factor of 10. So the low is a factor of 100 different from the high resolution here, and nevertheless we get a reasonably good convergence. So Paul Torrey is, who was also co-author on that paper, is currently exploring cosmological simulations, really uniform box simulations of this. I don't have any results yet, but we believe that, there's still some issues, but we believe that this should be working because we get these convergent results at these numerical resolutions.
There's a question in the chat real quick about whether the resolved wind models include cosmic ray driving.
So this model, the results I show here do not include cosmic rays. However, you can easily couple it to the cosmic ray model that is in AREPO. So I mean, we haven't switched that on, but you could do this. So there's, yeah, I don't have the plots here, but you could in principle do it. So, but we haven't done it for these specific runs. So these specific runs are really, yeah, a stellar feedback essentially without a cosmic ray component. Yeah. Okay. Good. And then at the end of the day, you can also make then an image of this galaxy. And this is one of these simulated galaxies with this new model. And you can now nicely see that you get very defined dust lanes and you know, get star forming regions. And if you look at it edge on, you also get a lot of details actually. Again, it's very similar to the fire model in terms of the details, but this, you know, the nice thing here is that this model should also work on these large volume simulations. At least this is what we hope, and we are currently working on that. So this is one direction. Yeah. So I think this is a very important direction to go for better ISM and feedback models that are less calibration dependent, because this model doesn't have, you know, just to point that out, the wind model that has been used in TNG and Illustris got, for example, properties of the wind were inferred from the surrounding dark matter halo. Yeah. And this is also explicitly discussed in the TNG and Illustris papers. So this is not the case here anymore, right? So this is really purely self-consistent. So in the sense that there is no information fed from the halo into the wind model or whatsoever. So that self-consistently comes from the supernova driving in these simulations. Good. Another thing that we are also currently working on, which is, well, there's nothing published even on that. So this is really something that's ongoing since 1.5 or 2 years now, but you know, we are still working on that, and that's work mostly led by Raoul Canan, who was a postdoc of mine at MIT, who's now at CFA, and by Aaron Smith, who is a postdoc at MIT, and Enrico Graldi, who's a postdoc at MPA, and other people involved are Rüdiger Packmore, Volker Spring, me, and Federico Marinacci. So this is just something completely different now. So this is really about high resolution cosmic reionization simulations. And so this is the so-called Thiessen project. So the idea here is that we take essentially the Illustris TNG model and then couple it to a radiative transfer that Raoul Canan has developed at MIT a couple of years ago, and couple that also to a new description of dust physics, and put this all together to do essentially high resolution reionization calculations. And so in these simulations, so this is just a summary of what goes into that. So as I said, it's based on Illustris TNG, so it's using AREPO and all these other things. But then on top of that, it's also having this efficient radiative transfer scheme where we inject photons from stars, including modeling of binary systems, but also QSOs. We do this multi-species non-equilibrium chemistry. So all this has been developed by Raoul over the last couple of years. And then we have also a dust model, self-consistent dust model that tracks essentially the creation of dust and the destruction of dust and all the growth aspects of dust, and also the interaction of the radiation with the dust. Yeah, so that's also incorporated. So that's a model that has originally been developed by a graduate student at MIT, Ryan McKinn. And both of this has been put together in these simulations. And as I said, we're still working on that. Cannot show you too many results yet, but so this is just as a comment on the dust model. so we modeled self-consistently here the accretion and sputtering in a dust-gas interaction, but then there's also shattering and coagulation in dust-dust interactions, and also dust production and the interaction with supernova shocks. So all this is put together to kind of mimic and simulate the whole dust life cycle in galaxies. What you then get, so these are just from some test simulations, some light cone images starting at redshift 17.7 down to redshift 5.5. Here, dark matter density, gas density, the ionization fraction, and the gas temperature. Yeah, so of course there's a lot of science we can do with that, but so this simulation is still running. So in terms of the numerical parameters, so the volume, the box has a side length of approximately 100 megaparsec, and the mass resolution is a bit better than 10 to the 6 in dark matter mass. So that's slightly worse than TNG 50, but getting pretty close to that. Of course, we don't run this to redshift 0, so we will probably run this to redshift 5 or so, or maybe a bit below. But the nice thing here is that the underlying galaxy formation model has been used and has been studied at lower redshift. So we know that the galaxies that are forming here are the correct progenitors of a redshift 0 population that leads to a correct galaxy population. So that's a huge advantage of that model, because the TNG model has been tested so well over the last couple of years. Good, and here are some, well, these are just some basic results. So as I said, I don't have too much. There's some tau CMB here, but then what's probably even more interesting is these self-consistent UV luminosity functions in terms of M1450 at different redshifts, so 8, 7, and 6. Of course, this is all based on some test simulations, but you can see that it's not perfect, but it looks already quite encouraging. And the same is true if you look at the dust abundance. You can also check this as a function of stellar mass here, plotting the dust mass, and similarly plotting the dust to metal ratio as a function of metallicity here. Yeah, so again, I wouldn't say that this looks perfect already, but it's at least encouraging, so that we are more or less on the right trajectory. And so this is something that we are pushing now. So the simulations are running at the moment. So they are running in Germany, in Munich, and so we hope we have some results in a couple of months here.
Another question in the chat about the dust populations, pointing out that historically, it was a problem that dust destruction was actually too efficient, and wondering whether that's no longer a problem in these models.
Yeah, so that's a good point. So the dust, let me just see. There is still a problem with the dust, in the sense that so the dust still has a couple of free parameters. For example, we have to parameterize somehow the growth, for example, and the supernova destruction rate and all these things. And for example, if you set up the dust model to produce the dust mass function at redshift 0, and you then look at redshift 2 or 3, then you find that it's not consistent. So it's this old problem, essentially, that having a dust model that gets the low and the high redshift right is just difficult. So also this model doesn't solve that. So the way we did this now, this is essentially tuned in the specific run to produce the, what we know about the high, well, in quotes, high redshift dust abundances. But this model, if you would run it forward, would then not agree with the redshift 0 results. So that is a caveat. And this is, you can look at these McKinnon papers. So there's a paper called Simulating Dust Successes and Failures. And there we discuss in detail the issue with getting low and high redshift dust populations right. So this is still an issue here in this model as well. And we haven't yet found a solution for that. As the question points out, that was just asked, this is historically a quite severe problem. Okay, let me just move on. So then for the last, I guess, 5 or 10 minutes, I just want to talk about the cosmological frontier, so I will keep this rather short. So what do we mean by cosmological frontier? Of course, this could mean many things. And I just pick only one aspect here. And the aspect, well, before picking the aspect, let me just clearly state what I actually mean. So if you go back to the beginning of my talk, I showed this overview of all the cosmological simulations. And actually, if you look at these papers, all these simulations assume that the lambda CDM paradigm. Yeah, so there's none of these big simulations ever ran anything else than lambda CDM. And of course, also assuming the canonical form of gravity in the form of general relativity. Yeah. However, as you know much better than I do, there are still a lot of discrepancies between theory and observations. That is true for the structure of galaxies, but there's also carries on to things like the H0 discrepancy and many other things that actually makes you wonder whether the framework is correct. Is the lambda CDM framework correct, and is gravity really behaving the way we think it behaves? So there is some value to explore these kind of alternative cosmologies in terms of alternative dark matter models, alternative dark energy models, and alternative gravity models. And of course, with these simulations, you can very nicely do this because you just change the way how dark energy works. Like you get rid of a cosmological constant and use some other, for example, quintessence model or early dark energy model or whatever, and just see how structure formation proceeds and what kind of universe you get. And the same is true with gravity, right? You could do some f of r gravity or other forms of gravity and just explore this. And there are of course simulations that do this, but it's really a tiny fraction compared to the overall number of studies and simulations that have been done. So, and I think there's a bit of a problem because lambda CDM is of course very well tested, but it might still have issues. And so I think it is, especially now, probably even more interesting than a couple of years ago to really study also simulations of alternative cosmological frameworks. Now, in principle, that means you can vary the nature of dark matter, the nature of dark energy, and the nature of gravity. So I will now focus only on one aspect because I have only worked on one of these aspects, and that is the nature of dark matter. So as all of you know, we believe now that CDM is the right theory. At least most people believe that. Now, historically, there have been a lot of what people call small-scale CDM problems, and I guess all of you have read these terms here hundreds or thousands of times in talks and in papers. So all of these classical small-scale CDM problems. Some are a bit newer, some are a bit older. Like the oldest one is probably the missing satellite problem and core cusp problem. And then we had 10 years ago the too big to fail, and then 5 years ago the diversity problems, and a couple of years ago the plane of satellite problems. So all these are problems, but then at the same time, many of these problems have been studied in detail, especially in the context of hydro simulations, and some groups could quite convincingly demonstrate that some of the problems, maybe even all of the problems, can potentially be solved through baryonic physics. So, this essentially implies that whether this is really a problem or for CDM or not is a bit unclear, because it might just have to do with the baryonic physics. But I think independent of this question, there is another question or another problem that is not on this list, which I think over the last 10 years again became more pressing, and that is the fact that this simple idea of a CDM particle in terms of a WIMP or other generic CDM particles, I mean, none of these particles have been detected so far. So I think this is getting more and more serious, this problem. I don't think it's yet at a very serious stage, but as time goes on and as detector experiments go on and nothing is found, at some point it will become more serious. And so I think it's just interesting for that reason alone to explore alternative dark matter models and just see how structure formation proceeds in these models. And of course, as soon as you go away from CDM, then there's this enormous number of dark matter models that you can study. And this, of course, we cannot simulate all of those. So I will only show a few interesting cases here. And one is this set of ethos models. So what is that? So ethos is not only a set of simulations, it's actually a whole framework that has been developed by Francis Seracin, Jesus Zavala, and a couple of others. And the idea here is really that you take a fundamental dark matter model, just a particle physics model, and you map this model to an effective structure formation model, where the effective structure formation model is described by only two things. One, by the initial transfer function, and second, by the self-interactions between dark matter particles. Yeah? And what that allows you is to partition essentially the large space of particle physics model into blocks of effective structure formation model. Because for structure formation, for galaxy formation, not every little aspect of a particle physics model actually matters. And you can bunch some of them together according to these effective parameters. So the whole theory has been worked out in this paper by Francis Jan Seracin, so in case you're interested. So since I'm not a particle physicist, the only thing I did was actually to simulate some of these models, and this is in this 2016 paper, and some of these results are shown here. So this is, for example, a comparison of a Milky Way like halo dark matter between some of these effective models, ethos 1 to 3, and the CDM case. And it looks a bit like a warm dark matter simulation. This simply has to do with the effect that the models we picked had a pretty strong suppression in the initial power spectrum. But that's just a specific feature that we picked here. You can also have other models. So I think that's a pretty interesting class of models, and there have been a lot of papers been written on this ethos models that you can find on the archive. Another thing that is interesting that I also want to point out, at least it's interesting to me, is to go a bit away from these standard SIDM simulations that have been done over the last 20 years, starting from the first studies of, when Spergel and Steinhardt put this idea forward. All these simulations over the last 20 years, at least the vast majority, assumed that you have always elastic interactions between two dark matter particles. So what Tracy Sletyer and Kathleen Schutz have actually explored, they explored models that can easily written down for inelastic interactions. And what we then did, so here's Zavala and me, we simulated some of these models, and just want to show you some examples, or one example here, where we have a two-state dark matter particle with a ground state and excited state, a certain energy splitting, and endo and exothermic reactions and a certain ground state mass. Now, if you simulate such a model and compare this to the elastic counterpart, you get actually some interesting effects. So, for example, here you see the density of the dark matter, and I don't know, I hope this comes through over Zoom, but the inelastic case looks just a bit more fuzzy. So it's not as sharp as the elastic case. And you can also see the difference if you look at the density profile of subhalos here. So this is just for some subhalos, the dark matter density profile for CDM, the elastic SIDM, and the inelastic. And what you see is that the core density is actually lower in the inelastic. And the thing that I should say is also that the cross-section setup for the elastic and inelastic is the same. So the cross-section strength is the same, or value is the same, but nevertheless, you get a stronger density reduction here in the inelastic case. And so what's happening in this specific inelastic model is that you get kind of an evaporation effect of the halo cores. Yeah? So you get these exothermic reactions, you get an injection of energy into the halo centers, and this drives dark matter particles out, in addition to what you typically already observe through the heat transfer in elastic SIDM models. Yeah? So this is kind of an effect that you only get in these inelastic models. Yeah. So we haven't yet fully explored these models. This was just some first simulations, I also think that that's yeah, quite interesting.
Mark,
yep.
Can I ask, like, you know, so to have this effect, I guess you need to have the, you know, the Chi2 excited states should be, you know, like, you know, must be populated, I guess, right?
Yes, that's a very good point. Yeah.
And so
yes.
why are they populated? Like, you know, why haven't you already, you know, gone to the ground state back in the early universe?
So you can actually, I think Tracy actually worked this out in their paper. So there's another paper by Caitlin and Tracy where they looked at these, I mean, at the theoretical basis. You can actually, so let me first say, it's true. The simulations here have been initialized such that, you know, a large fraction have been in the excited state, but you can also figure out the reaction rates and, you know, how quickly you would de-excite. And you can actually see by the redshift where we initialize the simulation, you can, I mean, I cannot prove it now to you, but you just have to look at that paper. You can show that not everything is de-excited, and you have some, you can have quite some significant population of the excited state. It's probably not as extreme as we have it here, because we have also, I think, some simulations. It's probably even the one you see here, where 100% are the excited state. That's probably too much, but it's also, you know, you can have a significant contribution in the excited state without de-exciting everything. If you go through the, you know, with the cross sections and through the scattering probabilities. So it's, yeah, so it
distribution isn't thermal, you're saying, I guess.
Yep.
Like,
Yep.
you know, there's some non-thermal population.
Yep.
Okay.
Yep.
All right,
I mean, again, you should look at these papers of Tracy. I'm really not the expert in that. I have to say I mostly relied on the outcome of these calculations to initialize that. But it is because Jesus and I also had this exactly that concern. So why would we even have any population in the excited state? But it's really it's possible, and it's also not any extreme case. So it's a realistic thing to assume.
Okay, great, thanks.
Okay, good. So the last thing, I'm sorry, I will finish in a second. So the last thing I want to say is that, of course, you know, given this impact on the density profile, this will, you know, if you have a significant inelastic component, it will also lead to some revisions of, say, constraints on dark matter cross sections. So what I mean here is that you might have heard about the statements like, you know, to solve the too big to fail problem with SIDM, you need a cross section of that size, or to solve the core class problem with SIDM, you need a cross section of that size, simply because the suppression and density and the core radius are just correlated with the cross section of the dark matter. Now here, as I said, the elastic case and the inelastic case have both the same cross section, but nevertheless, I can create a lower density core for the same cross section. Yeah, so these cross section requirements on, you know, on solutions to small scale problems through CDM are actually different once you have a significant inelastic component. Of course, we don't know whether, you know, how much dark matter is inelastic and whether there's any even SIDM component, but the statement is if you have a significant SIDM component that is inelastically scattering, like in a model like that, then the cross sections you need to create significant cores are much smaller than what you typically would assume if you had only an elastic model. So that is what is meant by this little box here. Okay, and then the last slide before I come to my conclusions. I'm really sorry that I run over time, and I keep this very short. It's just another interesting idea that actually I'm not too much involved in. Well, maybe a bit, but that's mostly driven by Philip Mosch, who's currently a postdoc at Princeton. So he has now, you know, quite some number of papers on this fuzzy dark matter. And, you know, this is a very interesting type of dark matter because it behaves so differently from what we are used to. Essentially, the interesting aspects are that it's ultralight axion with a very low mass, so low that you can actually see quantum effects on quite large scales. So you can get quite large de Broglie wavelengths of, you know, in some models even of a KPC, and then you get interesting effects like cores in halos that are stabilized through quantum pressure, and also what you can see here, you can get quantum interference effects in filaments. So a lot of things look very differently, and you know, these these models are numerically not very well studied yet. So Philip has done in a recent PRL some studies of the first structures in the universe in these ultralight axion models, where he also coupled this to hydro. But beyond that, in the galaxy formation sense, not much has been explored. So I think there's a lot of interesting questions related to that. Unfortunately, it's numerically not so easy to do these calculations, because you cannot just do ordinary n-body. But I think there's a lot of interesting theoretical, especially theoretical questions related to that. How structure formation in such a model proceeds. Good. So then I come to my conclusions. So I keep this very short. So I hope I could convince you that the most recent simulations, large volume simulations, are now work pretty well in reproducing observational data. I only showed you a few examples, but you can go to the Illustros or Illustros TNG website or the Eagle website or any other of these projects to see that really, these effective models do a pretty good job in reproducing a lot of observational data. Now, I think there are, beyond that, two main frontiers. So I talked about this astrophysical frontier and the cosmological frontier. Astrophysically means coming up with better models to really have, with the overall goal to get into this approximate ab initio regime, and the cosmological frontier, meaning that I think it's important to explore alternative cosmologies with these simulations as well, and not, put all your money on lambda CDM, but really, keep open-minded and also explore some of these alternatives. And yeah, I stop here. Thank you.
Thanks, Mark. That was great. We had, so yeah, we actually, I would say this is about exactly to time, because we did start a few minutes late, and you got plenty of questions along the way. So this will be the official end of the seminar slot. However, we do have a little bit of time blocked out afterwards. If anybody has lingering questions or would like to stick around and discuss a bit more, that's fine. Otherwise, we'll see you later.
Okay. Thank you.
I actually have a quick question.
Yep.
Which is, this is maybe more of a big picture question. So you're talking about these two main frontiers and sort of the theoretical or modeling innovations that are driving those frontiers. And I'm just wondering, when you're looking at the big picture, is it really innovations in modeling of the sort that you're talking about that are kind of the limiting factor in moving the field forward, or like to what extent is something like computing resources a limiting factor? Is that less of a concern at this point in time?
Yeah, so I mean, I think both is important. I mean, the modeling, how to really implement all this baryonic physics, and at some point the question of cosmic rays came up, right? So I haven't talked about that, but the actual driver of stellar feedback, we still don't know that exactly. Is it mostly driven by, or is it, to what degree is it driven by cosmic rays? To what, what are the main drivers, and how to incorporate those? So there's still a lot of open questions. So the modeling is definitely very important, but of course at the same time we also want to have, I mean, to get better models, you often need higher resolution, because if you want to have a more fine-grained model, you need more detailed information about your physical system, and that typically means you need better mass resolution, better spatial resolution. And I think the limiting factor at the moment, I mean, there's a lot of people working on the modeling, but there's not a lot of people working on the, on how to exploit actually upcoming supercomputers. So, and in fact, there's only, I mean, to be honest, I think there's only a very small number of people who can actually even do this, right? In the sense, how do you parallelize over 1 million cores or so? I think there's, I mean, I'm definitely not one of these people, but there are maybe a handful of people that can do something like that. And Volker is one of them. And so, the field relies on some of these people to also push the codes to these large core counts, where we then can also really run at a resolution level where it's even possible to model things in detail, right? So I think it always goes hand in hand. And so the progress, I mean, if you look at the simulations that I presented, the progress there in terms of what they can reproduce and how they agree with the data also came always through a combination of better modeling and going to higher resolutions. So I think both is equally important, but I think the scaling to large, I mean, this technical aspect, like scaling the codes is, I mean, not so many people are working on that, and it's a quite challenging problem, I think.
Great, thanks. We have a hand up from Hanno.
Hey, yeah, that was a very nice talk. Thank you.
Thank you.
I have a question to you, not as someone who necessarily runs these simulations, but who's someone who's written this review article. You have this really nice table about all those simulations that were run. So it really seems like an enormous industry that's built around here. Do you worry at all about the carbon impact of these sort of runs? Because I did a quick back of the envelope calculation of like the 200 million core hour one that you mentioned earlier. That's equivalent to about 2,000 intercontinental flights. So looking at the list of, a long list of these sort of simulations, we're probably talking about millions of intercontinental flights that go into these sort of simulations as a global community. Is it organized in the most efficient way, or is this industry that has been built up there sort of just a self-reinforcing industry without actually, maybe it could be done more efficiently?
Okay, so I mean, I guess this talk is recorded, right? So I have to be careful what I say. No, I think you're right. I don't think it's done in the most efficient way, right? So because, of course, every group tries to run their simulations and push them to the maximum, and that means, and I fully agree with this carbon footprint statement, that means that, today's simulations are typically run on the order of 50, 100,000 cores, right? And you run there for months. So it's enormous investment in terms of, compute time, but also in terms of money, but also in terms of the carbon footprint. So I think eventually this will probably be organized in a more efficient way, where maybe groups try in and build larger collaborations. I mean, there are already larger collaborations. For example, in Europe, there's the Virgo consortium, which has a lot of members and which just runs one big simulation every couple of years. So maybe that's the model forward. So I don't know, but I fully agree with this carbon footprint thing. And I don't know how it's at other institutes, but I've seen this recently at MKI. So at the Kepler Institute at MIT, we actually summed up how much carbon was actually produced by various activities, including real flights, but also the computing effort. And I don't know, I guess this has to be optimized. On the other hand, there are also some, the computing centers themselves, they also want to reduce their carbon footprint. So they try to use different forms of energy. So for example, the Harvard has a large computing center that's built next to like a water dam where they use the energy of the water, and so it's pretty green. But yeah, for sure, with the global climate movement, for sure there will be different solutions coming up. So I agree. If you look at the table and calculate the numbers, it's probably a shocking number of CO2 emission. That's the way it is now, and it's probably not the most efficient way. Yeah.
Chris is pointing out in the chat that having GHG statements, which I'm guessing stands for greenhouse gas statements, at the end of computing papers is a good first step.
Yeah, I agree. I mean, I think for everything you do, transparency is always a good step. And to be honest, if you just bring up another aspect now in these strange times of none of us traveling anymore, I think, this is also a huge carbon footprint. I think actually in the time being, or for the next couple of years, we will probably do also more online and fly less, and maybe have even more virtual conferences and so on. So I think overall, our field has not paid much attention to that. And I fully agree that transparency in terms of a statement in the paper is a first important step, because once it's printed and people see it, then people will pay attention and try to reduce it. Yeah.
I see a hand up from Dick.
Hi.
Hi.
Hi, Mark.
Hi.
So the Volker and company just released Gadget 4, and one of the aspects of a repo was, a repo is great, and the Gadget line is kind of passé, but with the improvements in SPH and other similar methods, those things have come back to the fore. I wonder if you could comment on the suitability of Gadget for calculations, and why you would say a repo is by far better, and is it for all sort of approaches to these problems in terms of computer time and other things.
Okay, I mean, I mean, of course, the best person to ask would be Volker here, but the point is, it's true. There have been a lot of improvements in SPH, and also there have been a lot of new mesh-free methods, and there have been the Gizmo code and a lot of improvements, so that if you take modern SPH codes and compare them to the traditional ones from 10 or 15 years ago, I mean, there's just enormous differences between those in terms of what issues they have, like all of these a lot of the major limitations of SPH have been compensated in these newer versions of SPH, and as you correctly pointed out, Gadget 4 includes a lot of these improvements and has this fully fledged SPH implementation. I still think that that the moving mesh approach is still probably more precise if you really do detailed testing of the benchmark tests for hydrosolvers. It's probably still superior to some of these. But what's definitely better in Gadget 4 than what we have in Arepo now is the overall parallelization strategy and the scalability. So if you want to run a very, very large box with an enormous number of particles, say n-body in the multi-trillion particle regime, then Gadget 4 will definitely outperform Arepo at the moment, because Volker has implemented a lot of work in scalability and parallelization. Then there is the new gravity treatment, which is not purely tree anymore, but fast multiple methods. So a lot of things that are just making the code much more efficient and much more scalable. And depending on your application, SPH might also be perfectly fine, especially if you want to run very large volumes, and you just need you don't want to resolve super small scale ISM physics, but just get an overall box with rough hydro properties. It's perfectly fine. I think what's happening on the long term is probably that the Voronoi tessellation stuff and the whole hydro of Arepo will be put into Gadget 4 and eventually replace the SPH part. That's my guess, right? Because the main advantage of Gadget 4 is really the extraordinary scalability and the code performance for doing the gravity and other things. So that's really way better than what we had in Arepo or Gadget 3 or any of the other codes. And so they ran already some very large dark matter only simulations with Gadget 4, way larger than what we had done before. And there the scalability really pays off. And also things like dynamic range. There has also been a paper, I forgot the first author, but Saunak Bose and Volker and a couple of others were on this, where they looked at the smallest first mini halos, this Halos in Void project, where they kept zooming in and zooming in. And also for these kind of applications where you need enormous dynamic range, also there, Gadget 4 is better because it has a new approach for the coordinates and so on and so forth. So I think it's a great code, and the SPH there is state of the art, and yeah, I would use it for a lot of things, but yeah, I still believe that if you purely benchmark the hydro, that Arepo is in terms of the pure hydro scheme, still better. But that's also a bit of a philosophical discussion, right? So the question then always is, how important are these detailed effects for galaxy formation, where you anyways have a lot of other issues interacting with the hydro, like all the feedback and so on, and where a lot of other uncertainties come in. So that, yeah, that's then, yeah, it's a matter of debate, essentially.
Yeah, so, well, actually, I think it's just wonderful that there have been some improvements, and I agree with what you said about the switches on Gizmo. Also, gets it up there. What about the Ramses operation and a sort of a spin-off of that? Not quite a spin-off. The largest flagship simulations for Euclid were done in, well, as you know, in Switzerland, and they do all sorts of specialized, very large cores. Is Gadget 4 capable of doing things of the magnitude that?
Yeah, I'm pretty sure it is. I mean, I can't say for sure, but according to the numbers I saw and the scalability that I saw, I mean, just to give an example, so they have now ported some of the Gadget 4 improvements also into the Arepo code for scalability, and they run now Arepo in a good scalable regime up to I think on production on 150,000 cores. So yeah, I'm sure it works as well as the. I mean, I don't know the Ramses code in detail, but I think it should be at that level at least. Yeah. Because the Gadget 4 was specifically tuned to really very large n-body simulations. So that was one of the prime goals, to do extremely large n-body runs.
Good.
I see Martine's hand up in the chat, and I was going to say, maybe we can make this the last question, just because I know it's a little late where you are, Mark.
That's okay. I can.
Yeah.
I go late to bed, but it's okay.
Okay, thanks. Yeah, so I was wondering, like you had been mentioning earlier, some of these discrepancies that we see between lambda CDM simulations and real observables are potentially attributable to baryonic effects that we just don't understand that well yet. And I'm wondering if that's still a major concern given all of these updates, and whether you think that testing beyond CDM and also beyond lambda models is sort of reliable, given that probably not all the baryonic effects are perfect. And I guess which ones would have sort of a smoking gun signals that couldn't be confused with baryonic effects?
Yeah, that's a good question. So I don't have a precise answer for the last question. You know what could be a smoking gun, and I think, yeah, I would need to think about this in more detail. I mean, because the problem is also a bit that different SIDM models and different baryonic physics implementations lead to different imprints. So to have a definite statement, yeah, I guess this requires some thought. Now, coming back to the first part of your question, you know, on this consensus that baryonic physics can actually solve all these small scale problems. I mean, I mentioned that this is now the general idea in the field. However, this is only true for a subset of the simulations and for a subset of the galaxy formation models. So so for example, if you take the Auriga models, so they don't see the same effects as the fire simulations, for example. Of course, it always depends on, you know, what's your density threshold for star formation and the efficiencies and all these things, they matter a lot, but it's not that, I mean, the statement is not that all the hydro simulations give the same result. Even if you try to make them similar in terms of, you know, their behavior, it's just not always giving the same result. So even the solutions that we find for some of these small scale problems, they work for some simulations, but not for others. And then there are different ways to argue around that, but I don't think that we are at a stage where everything is where there's a full consensus that, okay, that these small scale problems are all hydro or baryon physics related. I think there's a certain likelihood for that because a lot of people have demonstrated it. But whether you solve all the problems with this and whether all baryonic physics models really make these predictions and lead to the same solutions, I guess that's still, yeah, not yet fully settled.
Thank you.
Yep.
All right. Well, thanks very much for your talk and for sticking around to answer questions, Mark.
Okay,
We really
thank you.
appreciate it.